So the first speaker of this session is Takahiro Sagawa, and he's going to speak on quantum fluctuation theorem with continuous measurement and feedback. Screen sharing is working. Full screen.
You see the screen?
Yeah, that's perfect, I think.
Okay.
Okay, over to you. And I'll tell you when there's 2 minutes plus 5 left.
Okay. I'd like to thank the organizers for inviting me to this workshop. Today I'm going to talk about fluctuation theorem with some information processing processes, especially with continuous measurement and feedback. Okay, so this is the collaborator. They are collaborators of this research. The main player of this project is Toshihiro Yada. He's a master course student of my group, and this is published in this paper. But today I'd like to make a bit long review about the background of this research, and then I will go to the main result. And let me start with the very general introduction to this topic about the thermodynamics of information. Okay, so the basic background of this research is thermodynamics of information. For example, there's a very old thought experiment called Maxwell's demon. And if the demon performs a feedback control by performing a measurement and feeding back the obtained information to the system at the level of thermal fluctuations, then the second law of thermodynamics is apparently violated. But the important point here is that we should take into account the information contents, like the channel information or the mutual information, as a part of thermodynamic entropy. Then we can recover the consistency between the demo and the second law of thermodynamics. By considering this kind of stuff, we can understand the foundation of the second law of thermodynamics, and also we are interested in applications to nanomachines and nanodevices. And the prototypical model of Maxwell's demon is known as the Szilard engine. So this is a minimal model of Maxwell's demon that demonstrates the quantitative connection between the work and the information. For example, we can imagine that there is a box and there is a particle in the box, and the box is in contact with the heat bath at temperature T. And then we insert a partition at the center of the box, and then the demon performs a measurement about the position of the particle. And the demon found the position of the particle left or right. By this measurement, the demon gets 1 bit of information, that is log 2 of information in natural logarithm. Then the demon performs a feedback control, and if the particle is found in the left side, then the demon does nothing. But if the particle is found in the right side, then the box is moved to the leftmost position. And finally, the box is expanded very slowly, quasi-statically and isothermally, and the demon extracts KT log 2 of work from this isothermal expansion. So this is a kind of cyclic process. So it is apparently similar to the perpetual motion of the second kind, but actually it's not. So the essential mechanism of this feedback information engine is that the entropy of the system is decreased by the measurement and feedback. So if you compare the entropy of this state and this pre-measurement state, then the entropy of the system is decreased by log 2. And it means that the free energy is increased by KT log 2, and that free energy increase is extracted as a work in the final expansion process. So the important point is that the demon can control physical entropy by using information. And nowadays, there are many experimental demonstrations of Maxwell's demon, like by using colloidal particles or single electrons, and many other systems, including quantum systems. And theoretically, there are many extensions of the fluctuation theorem and the second law of thermodynamics by incorporating information terms. For example, the simplest setup is the classical system with a single measurement and feedback. So in this case, the mutual information appears, and by using that, we can derive the generalized second law. and it's one of its extensions is the case that the measurement and feedback is continuous in time, and then a continuous information flow called the transfer entropy appears in the second law and the fluctuation theory. And also another direction of the extension of this classical result is the quantum system, where the quantum measurement is performed on the quantum system and feedback is performed at the level of quantum fluctuations. In this case, we need some extended notion of mutual information to the quantum region that we call the QC mutual information. And what is remaining is this region where we consider the quantum measurement and feedback in continuous time region. So in this case, we should introduce a new extension of the quantum information to the continuous measurement and feedback regime. And this is the main target of this talk. But before going to here, I will talk about these three cases step by step, and finally I will go to this main result. Okay, so let me start with the classical case. Okay, so the basic information content is known as mutual information. So we consider the system and the memory in which we write in our measurement outcome. So, and then the effective information that is obtained by the measurement outcome is described by the mutual information like this. Here, H of S is the channel information of the system, and H of M is the channel information of the memory, and H of SM is the joint channel information of these systems. And the mutual information satisfies these two inequalities, and essentially it describes the correlation between the system and the memory. And by using that mutual information, so we can generalize the second law of thermodynamics. So there is a heat engine, and if there is no max-rate lemon, then the upper bound of the extractable work is bounded only by the free energy difference. But if the demo gets the mutual information I and performs a feedback control on the system, then the upper bound of the extractable work is given by the mutual information multiplied by the temperature and the Boltzmann constant. So this is a generalized second law by incorporating information term, and this information term and these energetic terms are treated on equal footing. And another important point is that the equality here can be achieved in thermodynamically reversible limit. This ensures that this is a kind of optimal natural extension.
Question, so does the free energy contains the free energy of the measurement device?
Sorry, I couldn't hear. So could you repeat again?
Does the free energy here that actually contains the free energy change of the measurement device?
A free energy, sorry. Maybe
I think he's asking about whether the free energy includes the measurement device.
Oh, this free energy is the free energy of the engine itself. The free energy of the memory is not included here. Is that
so I wonder if the information of the demo is equal to the free energy change of the measurement device.
It's not necessary. So yeah, it depends on situations, but yeah, it's not so simple. But sometimes, yeah, you are right. So the free energy increase of the measurement device equals the mutual information. Sorry, it's opposite. So the decrease of the free energy in the memory equals the mutual information. That is kind of optimal case. Is that?
I think you should carry on.
Okay, thank you.
Okay, so this is the second law at the level of ensemble average. So this work is averaged work, and this free energy is, of course, ensemble averaged concept. On the other hand, the Jarzynski equality or the fluctuation theorem is a very important topic in stochastic thermodynamics. And without a measurement or feedback, the ensemble average of exponential minus beta double minus delta f is always given by 1. So this universal equality is always true, even if the system is far from equilibrium. But if we perform the measurement and feedback, then the original Jarzynski equality can be violated. So in that case, for example, if there is a Maxwell's demon, the left-hand side without this information term, it's deviated from 1. So that is a kind of a violation of the Jarzynski equality in the presence of Maxwell's demon. So in order to recover the Jarzynski equality, so we need to incorporate the information term inside the ensemble average. So this I is the stochastic version of the mutual information. And if you take the ensemble average of this, we recover the original mutual information as this. So by introducing this stochastic mutual information to the Jarzynski equality, we recover the universal form of the fluctuation theorem that this ensemble average equals 1. So and by applying the convex inequality, that is the Einstein inequality here, and then we reproduce the average second row like this. So this is the same as that I showed before. Okay, so this is the formulation based on the work and the free energy. And there's also a slightly more general formulation based on the so-called entropy production. In this formulation, we introduce the stochastic version of the channel entropy and the heat instead of the work and the free energy. So, for example, in this case, X is a system state and Px is a probability of that state. And this small s of X is a stochastic channel entropy. Its ensemble average is just ordinary channel entropy. And stochastic entropy production is given by the difference between the stochastic channel entropy and the stochastic heat divided by the temperature of the heat bath. In this case, the heat is defined as the heat absorption by the system from the heat bath. Okay, so and if the system is in summer equilibrium at the initial stage, then this entropy production is given by just the difference between the work and the free energy. And by using this stochastic entropy production, we have the integral fluctuation theorem. So this is very similar to the Jarzynski equality, but it is slightly more general because we allow the initial and final non-equilibrium states for the system. And then by applying the Einstein inequality to this, we have the second law of thermodynamics at the average level that states that the ensemble average of the entropy production is always non-negative. Okay, and again, we can incorporate the stochastic mutual information here. And if there is measurement and feedback, we need to introduce the information term inside the ensemble average. And the generalized second law is given by this. So the entropy production can be negative up to minus of the mutual information. So this is a slightly more general form of the generalized Jarzynski equality and the general second law of thermodynamics. Okay, so this is a scenario of a single measurement and feedback. Then the next step is to generalize this result to the continuous measurement and feedback. So that is particularly interesting because, for example, in cells or bacteria, so we have some autonomous information processing. So there is no external agent that perform just a precisely single feedback or measurement. But everything is autonomous and continuous in time in biological systems, typically. So we need to extend our theory of thermodynamics of information to continuous information processing processes. And for that purpose, we need to introduce a continuous version of information flow. So the mutual information is a kind of a snapshot, static concept that does not describe any dynamics, but if there is some continuous information flow, we need to introduce some dynamical version of mutual information. There are several approaches to this problem, and typically there are two major approaches. One is based on the transfer entropy, that is a kind of continuous information flow. And the other approach is based on the so-called information flow. So this is a particular information flow. And both of them have some advantages and some disadvantages. For example, based on the transfer entropy, we can derive a very general second law for including non-Markovian processes, but the second law is weaker in Markovian dynamics. On the other hand, by adapting this information flow approach, the second law is stronger in Markovian dynamics, but that is not applicable to non-Markovian dynamics. But anyway, so in this talk, I will focus on this transfer entropy approach because this is the straightforward classical counterpart of our main result in this talk. Okay, so this is a simple definition of the transfer entropy. So we consider a bipartite system consisting of a system X and system Y, and we imagine that system Y is a Maxwell's daemon that gets some information about system X, and the daemon performs feedback control on X. And we suppose that this is a continuous dynamics, and this figure just describes a single step of that continuous information processing from time t to time t plus dt. And what we want to quantify is the information that flows from x of t to y of t plus dt. So this can be characterized by the conditional mutual information. So this is a conditional mutual information between xt and yt plus dt under the condition that y of t is known. So this means the additional information that is newly obtained during this dynamics, because we have some conditioning about the past information about yt. And we can easily show that typically this becomes the order of dt, so we divide it by dt, and this is the transfer entropy rate. The essential idea is that we need the conditioning based on the past sequence of measurement outcomes, in this case, y of t, and if necessary, we need the conditioning in the sequence in the past direction. So this transfer entropy was introduced by Schrieffer in 2000 in the context of time series analysis. But more originally, so it was introduced in the context of economics, and it is closely related to Granger causality that got Nobel Prize several years ago. But anyway, so by using this transfer entropy, we can again generate the second law of thermodynamics and the fluctuation theorem. So this is again the stochastic version of the transfer entropy. And by introducing this into the inside of the ensemble average, and we have the generalized fluctuation theorem and the second law of thermodynamics. Its lower bound is given by the minus of the transfer entropy. And we have applied this to a kind of biochemical signal transduction that is chemotaxis of E. coli bacteria. And we have shown that in some model analysis, the efficiency of feedback group in the signal transduction pathway is characterized by this generalized second law and the transfer entropy. Okay, so this is a classical part. Then I will next go to the quantum part. Okay, so quantum thermodynamics is also a very interesting field, and there are many experimental platforms in which we can actually implement Maxwell's daemons by using some quantum measurement device and feedback control. And for example, trapped ions or superconducting qubit and single electrons and NMRs. So in these platforms, we can observe the quantum entropy production and also quantum information very directly. So from the theoretical point of view, we want to establish thermodynamics in the presence of quantum measurement and feedback. And so, and the first step is to introduce the quantum counterpart of mutual information. So there are several versions of quantum mutual information. So, but here we focus on the so-called QC mutual information. So this is a kind of quantum mutual information that characterizes the correlation between quantum system and the classical measurement outcome. Because if we perform a quantum measurement, and even if the system is a quantum system, our measurement outcome itself is always classical variable. So to characterize the correlation between the quantum system and our classical classical outcome, we introduce this QC mutual information. And rho is the measured state of the system and the density operator, and S is the von Neumann entropy. And pk is the probability that we obtain some outcome k here, and this rho k is the post-measurement state. That is the state, the conditional state after we get the measurement outcome k. And this QC mutual information satisfies these desired inequalities. And if the QC mutual information is 0, there's no information transmission from the quantum system to our measurement outcome. But if the QC mutual information equals the Shannon entropy, then the measurement is error-free and classical. And again, by using this QC mutual information, the same type form of the second law is applied to the quantum measurement and feedback control. So this is essentially the same as before I showed, but we only need to replace the classical mutual information to the QC mutual information here. Okay, so this is the background of this research. And then I'd like to go to the main part of this talk. Okay, so what I have shown is that the second law is always given by this form. The averaged entropy production is bounded by minus of some information term, and the generalized fluctuation theorem is given by this. And this I is a stochastic version of some information term. And in the simplest case, the information term is the mutual information. And if the measurement is continuous, the information term is the transfer entropy. And if the system is quantum, then the information term is the QC mutual information. And what was missing is here, and we want to generalize our result to the quantum and continuous measurement and feedback setup. And to address this problem, we need to generalize our information term to some QC transfer entropy. That is what we have newly introduced in this research. Okay, before that, I would like to emphasize that quantum continuous feedback control is a very important technique in quantum electronics experiments. So from cavity QED to circuit QED and in many other systems. And in such systems, by performing a continuous measurement and continuous feedback, we can prepare and stabilize desired quantum states against the external noise. So this is the importance of quantum feedback control in the continuous time region. And our purpose is to consider the thermodynamic aspect of such continuous feedback control processes. Okay, so this is a very brief summary of our main result. So again, the second law and the fluctuation theorem are given as usual, but we need to introduce a new quantum information concept that we named QC transfer entropy. And by using this, we have the same form of the second laws and the fluctuation theorem. And the QC transfer entropy characterized is some total information transfer by continuous measurement. Okay, so this is our mathematical setup. So we have the system that is in contact with a heat bus that is at inverse temperature beta. And that interaction between the system and the bus is described by a Lindblad form like this. And this LD is some dissipation operator, Lindblad operator between the bus and the system. And also, in addition to this dissipation term, we introduce the measurement apparatus that performs the measurement and also a feedback control on the system continuously. So that is again described by a kind of Lindblad form like this. And this My is a Lindblad operator that describes the effect of the measurement. But this time we have some explicit measurement outcomes in our memory. So this Lindblad term is decomposed to some stochastic trajectories based on our measurement outcome. And that is described by a Poissonian Poissonian random variable as this. So this is called unraveling in terminologies of quantum control theory. Anyway, important point is that our equation of motion is basically the Lindblad equation, but we have some random variable that is corresponding to our measurement outcome, and the entire equation becomes a stochastic equation, and that is called the stochastic quantum master equation. Okay, so then we define the QC transfer entropy. So this is an extension of the transfer entropy. That is the accumulation of the conditional material information like this. And the conditioning is given by the sequence of the past measurement outcome. And in this case, we have naturally a conditional density operator here, because this is a stochastic master equation is given by the conditional density operator, and the conditioning is based on the entire past trajectory of the measurement outcome. So we have very naturally the conditional QC material information here by using the stochastic master equation, and by averaging it over all trajectories of our measurement outcomes, then we get the definition of the QC material information, like QC transfer entropy here. So yeah, our main idea is that by using this unraveling based on the measurement outcome, we very naturally have a kind of conditional QC material information here. So, but this is at the level of ensemble average. So to formulate the fluctuation theorem, we need the stochastic version of the QC transfer entropy. So this is much more involved stuff, and it is not trivial how to introduce the stochastic version of the QC transfer entropy. And this is our idea. So originally we have our measurement outcome and heat dissipation, and this is what we called standard unraveling, unraveling of the original quantum master equation. And by using the Trotter decomposition, we deform this to this, and in this case, the measurement and the dissipation do not occur at the same time. But in the short time limit, they are of course equivalent. And to introduce the stochastic QC transfer entropy, we need to insert two additional projection measurements. So these are a kind of artificial things, but we need them because the stochastic QC transfer entropy includes such terms. So our idea is that immediately before the measurement and immediately after the measurement, we perform a projection measurement of the system with respect to the diagonal basis of the conditional density operators. So So this is very artificial because we need to know what is the density operator at this time and this time. But if we suppose that we can do that, then this is a kind of non-destructive measurement because the projection is performed with respect to the diagonal basis of the state. So if we take ensemble average over our measurement outcomes, then the state is not destroyed by this measurement. So in some sense, we can insert these projection measurements artificially in addition to the real experimental measurement outcome. And based on that, we can define the QC mutual information as this, and this P is the diagonal element of the density operators. And so as I mentioned, these projections are kind of artificial things. So we cannot do the entire process only by the real experiments. So we proposed a kind of experiment-numerics hybrid method where the heat dissipation and the measurement and feedback are performed in real experiments. But in parallel, we perform some numerical experiments and we perform the artificial projection measurements only in the numerical simulation. And then by doing the real experiment and the numerical experiment in parallel, we can get the full information about the stochastic transfer, QC transfer. Okay, so this is our numerical demonstration. So, for example, in this case, these orange circles describe the averaged entropy production, and they are negative. So this means that the ordinary second law is violated by the measurement and feedback. But the minus of the averaged QC transfer entropy is always more negative than the averaged entropy production. So we can confirm that the generalized second law is always satisfied. Also, we can check the generalized fluctuation theorem by performing that hybrid method only in our computer. We didn't use any real experimental setup, but in this case, this is a fully numerical simulation. So we confirmed that if we introduce the stochastic QC transfer entropy term, then the ensemble average of exponential minus something is always given by 1. So this clearly shows the validity of the generalized fluctuation theorem. On the other hand, if we don't incorporate the stochastic QC transfer entropy term here, then the ensemble average is deviated from 1. So this is a violation of the conventional fluctuation theorem in the presence of measurement and feedback. Okay, so this is a summary. So in quantum systems under continuous measurement and feedback, we have generalized the second law and the fluctuation theorem. And for that purpose, we have introduced the QC transfer entropy, and we proposed the experiment-numerics hybrid method. And so we have filled this missing region to establish the thermodynamics of measurement and feedback, including the quantum region. Okay, so these are references, including our previous researches. Okay, so thank you very much for your attention.
Thank you very much, Takahiro, for that rather beautiful talk. Any questions?
There's a question in chat.
There were maybe one or two in the chat. It would be good if whoever put a question in the
I have
chat.
a question.
Yeah, please.
Okay.
So just a simple question, I guess. Does your quantum one becomes the classical one in the limit where, I don't know, the density matrix would be diagonal? Does that happen? Is it the same thing?
Yeah, exactly. That's completely the same. Yeah.
It's the same thing. All right. Thank you.
Yeah.
Very nice work. Thank you.
Thank you.
Further questions? I do have one which is perhaps a bit basic, and as you probably know, this isn't my area at all. But when you do this continuous measurement protocol, you actually split it, you discretize the time.
Yeah.
But then what that seems to mean is that those things which you label with the y, little y, those are sort of infinitesimal measurements in some sense.
Yeah.
And I'm not quite sure what that means. It's something which leaves the system almost unchanged.
Oh, yes.
So maybe you could just say a little bit more about what one of these y(n)s is in relation to what maybe naively one thinks of as a quantum measurement, which is some kind of discrete projection onto a...
Oh, yeah. Actually, in this setup, the quantum measurement is very weak, and almost every time step, nothing happens. But at some point, some quantum jump occurs, and that jump is introduced by the Poissonian process. So we don't have anything for a long time, and sometimes it jumps, then again, we don't have anything. So that is a kind of Poisson process. So that is the reason why, even if we have some continuous measurement outcome, the information content is not divergent.
Yeah, I see. But I mean, it is possible to define a measurement like when you do squeeze states and things, where you don't really completely measure anything, or you just basically change an uncertainty limit on something rather than give it a precise value, right?
Yeah. So, for example, we shed a light to the atom very weakly. Then
yes,
the information about the atom is read out very, very weakly and very gradually. So, in every single step, so the obtained information is infinitesimal.
okay.
Yeah. So yeah.
Do we have further questions? There is one in the chat, so I mean, I don't know if this is to everyone, but may as well read it out if there aren't people waiting. So this is from Vishnu Sahita saying, this continuous measurement protocol could be used to verify Jarzynski or Crookes fluctuation theorem, ? And then, so what upper hand it gives and what advantage is it compared to using 2-point projective measurements? Is it continuous measurement, including details about information? So I'm not sure if that makes sense to you as a question. If it does, please answer.
Yes. So yeah, actually there are two aspects of continuous measurements. So one is this green terms. So this describes some external measurement and feedback. So that is added to the ordinary 2-point measurement scheme. So in addition to the 2-point measurement, we perform another feedback measurement and feedback to reduce the entropy of the system. So that is the effect of this green term. On the other hand, in this red term, this is also different from the 2-point measurement scheme. And because in the 2-point measurement scheme, we suppose that the entire system, including the heat burst, can be perfectly observed in the initial and final time steps. But in this case, so the heat burst is a kind of an external system that is only described by the Lindblad term. So we need to observe the quantum jump in the burst to detect the heat absorption or heat emission. So that's the reason why. So we don't use the 2-point measurement scheme, but instead we need the full information about the quantum jump in the heat burst. So
good. Thank you very much. There's time for one last question if anyone has got one. If not, thank you very much again, and we should move on to the next speaker.
thank you very much.
Thank you.